Okay, ready, Gabriel? Yeah. All right. So here we are. This is lecture 4. We're going to be continuing section 6.2, which remember is about trigonometric integrals and trigonometric substitutions. So part 1, I want to review, or not review. Remind you of some of the trigonometric integral techniques and do a few important trig integrals. Some of these are actually done, 2 of these are done as examples or mentioned as examples in the reading, and one is actually assigned as a homework problem. But, well, it's not assigned. It's in the book as a homework problem, but I didn't assign it. So example 1. The integral of tan x. Well, it's helpful to write this as sine x over cos x. And then think about doing a regular substitution. So not, nothing fancy. So it doesn't look like a nested function, but one thing that makes the function a nuisance is that there's this cosine on the bottom. So let's let that thing be our u. So we've got a new version of that green thing. And then, you know, the way I would do these in the fall, I'd get a new version of the dx. That's going to be 1 over u prime du. So that's 1 over minus sine of x du. So that's a new version of that red dx. So when you substitute all this stuff in, you get sine x over u times minus 1 over sine x. And then there's your du. The signs cancel and end up with minus the integral of 1 over u. And remember that this is ln, so this is minus ln of the absolute value of u plus c. And remember that ln of something, review, ln of a over b is ln of a minus ln of b. So in particular, ln of 1 over b is ln of 1 minus ln of b, but ln of 1 is 0. So if I have minus ln of something, that's the same as ln of 1 over that thing. So this is ln of absolute value of 1 over u plus c. Let's substitute back. This is ln of absolute value of 1 over cos x plus c. So that's our first review, or our first trigonometric integral. Example 2. Now remember that trigonometric integrals are just integrals that are just where the integrand is a bunch of trig functions. What about the integral of tangent squared x? Well, this is a wacky integral. Yeah, it's just wacky because it turns out to be almost nothing. It seems to be, it's deceptively simple. So we don't have an integral formula for tangent squared. But we can write tangent squared in terms of secant squared. Does anybody remember how to do that? Yeah?
Is it just 1 over secant squared? Yeah, you can remember.
Well, 1 over secant squared is just cosine squared. So remember, say it again?
Is it 1 plus secant squared?
Is it 1 plus secant squared?
Secant squared plus tan squared equals 1, right?
Yeah, so here's where you should just go back to the original. Right, so there's something like it's secant squared plus 1 or secant squared minus 1 or it's 1 minus secant squared. So go back to the Pythagorean theorem. That says cos squared plus sine squared equals 1. So let's divide everything by cos squared. So that first term is 1, and then 1, and this is tangent squared, and then this is secant squared. So tangent squared, it turns out, is secant squared x minus 1. Now, even if you think you can remember this formula, well, I wouldn't waste the bandwidth to try to remember that formula or this formula. Just remember this one, because I mean, if you remember this, it could be that you're remembering it wrong. So just go back to the source and know how to derive these formulas. Let me remind you, there are boxes of binders out in the hallway. You know, here's my binder of my organizational stuff for this course. Here's my binder of calculus problems. I do all those calculus problems, and I put them in this binder. And you know, it's getting pretty full already. That doesn't bode well for the rest of the semester. But I can't count the number of times in this notebook that I have little calculations like that. You know, just do them on the spot. Now, you can abbreviate them. C squared plus S squared equals 1, and you know, so 1 plus S over C equals 1 over C squared. So 1 plus T squared equals secant squared. You know, there are all sorts of ways you can make it a little bit less time consuming to do those. So I end up with this integral. Now the cool thing about this is secant squared is a basic integral. This is tangent of x. And the integral of 1 is x. And that's it. That's all there is to that integral. You'd think that that's going to be harder than that one over there, but it's not. It's weird that it's this simple. The integral of secant x equals, well, there's an amazing trick. See the book. In the end, you do something like, you do a u substitution like you did for the integral of tangent of x, but not until you've done a trick first. And so the result ends up being ln of secant x plus tan x plus c, ln of absolute value, that stuff. So it's a trick. So, you know, well, if it's a desert island trick where you're stranded on a desert island and as soon as you figure out this trick, you can get off the island, you're going to be stuck on the island because you would never think of this trick. I wouldn't have thought of this trick. So read the book. It's a cool trick. So that's a quick review of trigonometric integrals. Part 2 is basic trigonometric substitutions. So the idea of a trigonometric substitution, it's an integral that does not contain trig functions, but after you do a substitution, it does contain trig functions. So it turns an integral that's not a trigonometric integral into a trigonometric integral. So you take a regular integral and you get some substitution, and then you get, as a result, a trigonometric integral. That's the idea. So, example 4. Is this. Integral of square root of the quantity x squared minus 25, all divided by x, so we're going to make a substitution of some sort. Now the book presents this list of ways that integrals can look and then tells you what substitution you should make. And again, I would not recommend memorizing that kind of thing. It's just not worth it. You should figure out how to brew up these substitutions on the spot. So the idea is draw a right triangle with the square root term x squared minus 25 as one of its sides. So here's my right triangle, and I've got to make that be one of the sides. So here's a question for you. Do you think that square root term is going to be a hypotenuse or a leg? Marcy's got a hand up. There's some other hands up. I want to get some more hands in there. Yeah. Well, if that's the hypotenuse, then what would the legs be? Yeah, so what would be the hypotenuse?
X.
X. Why?
Because it's that, like, x squared minus 25 and has to be over x, and all of, like, SOHCAHTOA. You can put it.
Here's a better way of thinking of it. You can't take a square root of a negative number. So that thing inside the square root has to be positive. So that means x squared has to be bigger than 25. So x squared has to be the thing that's the hypotenuse. So x has to be the thing that's the hypotenuse. So that means the other sides are, well, one of them is this, and the other one is going to be, what's the other side going to be?
Five.
5. Yeah, so notice Pythagorean theorem, gives you that triangle works. So according to this, we get, well, 5 over x, this is theta in this corner, 5 over x equals cos theta. So that means x over 5 equals secant theta. So that means that x equals 5 secant theta. So that's the substitution that the book would tell you to use in this situation. When you get an integral like that, use this as a substitution. And here's where I'm saying, don't think about memorizing that you've got to somehow memorize it. When you've got that, you do the substitution. When you just build your triangle and figure it out. Now you might think, now that we've got a new version of x, then I'm going to substitute that in here. But you don't want to do that yet. You first want to get a new version of the dx. See where that leads you. So, dx d theta is going to be 5 times the derivative d theta of secant theta. So in other words, dx equals 5 times secant theta tan theta. So there's my new version of dx. That's what's going to go in place of that dx, all this stuff. Yeah. Oh yeah, d theta. So I've got a new version of dx. Now, what's the simplest way to deal with this term? Yeah.
It's the opposite over the hypotenuse. So the sine of theta is x squared minus 25 over x.
Exactly. So this is square root of x squared minus 25 over x. That's just simply sine theta. So we've got a new version of all this stuff. So again, even though we had a new version of x a while ago, wait and see, if you can knock off more than one term at once. So when I substitute all these things in, I get the integral of sine theta, then secant theta, tan theta, d theta. So notice, a regular integral, substitution, trig integral. This is the idea of a trig substitution. Now, let's write everything in terms of sines and cosines. So this is the integral of tangent squared theta. Now remember, we just did this a while ago. I just erased it, but this is tan theta minus theta, right? Wasn't that the integral that we did a while ago? You all have it in your notes. Is that correct?
Yes.
Okay. Now we have to sub back. This is tan. So tan theta is going to be this over this. But what is theta? I need to substitute back in terms of x. What's the simplest way to write x, or to rewrite x in terms of theta? Well, there are some options here. we get options for substituting back. Notice from that picture, we get that secant theta is 5 over x. So that means that theta is secant inverse of 5 over x. So I could put that here. That is what's going to go here. I could put that there. Yeah.
Theta is cosine inverse of 5 over x. So it would be secant inverse of x over 5.
Right, that's another thing. So we get that cosine of theta is x over 5. So I get that theta is cos inverse of x over 5.
So I think your 5 over x and your x over 5 are flipped around. Because then she would say that 5 over x.
Oh, yeah. There we go. X over 5. Thank you. So I could put cos inverse of 5 over x in this box. Or notice that tan theta is that messy thing, x squared minus 25 all over 5. So theta is going to be tan inverse of square root of x squared minus 25, all that over 5. So any of these things could be put in that box. It's pretty wacky. If you go to a site like, if you choose one of those and you put it in the box, and then you go to helpmecheatemlikeCalculusHomework.com, you might find that their answer doesn't match yours because maybe they have one of the other things in that box. I'm going to put the last one in. So, thing is, these three functions are not the same function. How can it be that they all can fit in there? How can it be that it doesn't matter? Yeah.
They all equal theta.
Well, but they look like they're definitely different functions, though. Yeah.
No matter what you put in, you end up getting the same answer for all? Wait, no, is it just because there's plus c at the end?
It's the plus c that makes the difference. These three things, they differ from each other by constants. So if I put that first thing in here, well, if I put this thing in here, and I think this is the correct one, well, then if I put secant inverse of x over 5 in here, it differs from this by some constant, but that's okay because there's a plus c in here. So that's a very confusing thing. All right. Example 5. This is a cool problem. The ellipse, there's an ellipse whose equation is x over a squared plus y over b squared equals 1. So that's an ellipse that looks like this. The x-axis intercepts are at x equals minus a and x equals a. And the y-axis intercepts are at y equals minus b and y equals b. So the total area is going to be 4 times the first quadrant. So all we have to really do is figure out that area. So that's going to be 4 times an integral. integral is going to be from x equals 0 to x equals a something. You need to get an equation for this curve. Well, let's figure out that equation. We get x squared, x over a squared plus y over b squared equals 1. So y over b squared equals 1 minus x over a squared. Now, this is, I'm going to write this a couple of different ways. This is the same as saying 1 minus x squared over a squared, and this is the same as saying a squared minus x squared all over a squared. So if I take the square root of both sides, I get y over b is the square root of all that stuff. A squared minus x squared all over a squared. I can bring out that a squared from the bottom, and it just comes out as an a. And then if I multiply both sides by b, I get this. Finally, y equals b over a times the square root of a squared minus x squared. That's the formula, that's the function that describes this top leg of the ellipse. Now you might wonder why you'd present the ellipse this way when you could just present it as a function. But remember, this ellipse can't be described by a single function because it flunks the vertical line test. There is no formula that will give you the whole ellipse. There is an equation that will give you the whole ellipse, but there's no function that gives you the whole ellipse. This works because I'm taking only the positive square root. So I get b over a times the square root of a squared minus x squared. So I pull out the b over a, 4b over a times the integral from 0 to b. And we're stuck now with an integral that does not look like a trigonometric integral. There's no trig function in there. But we're going to do a substitution that will turn it into a trig integral. So here's my right triangle. Somebody tell me, raise your hand if you know what the hypotenuse should be. Liam? Good. Because in the square root term, that's the thing that's the bigger term. So then that square root term is going to have to be one of the other legs, one of the legs. And what's going to be the third leg? X. So I'm going to put x here. So in this picture, you can see that x over a equals sine theta. So x equals a sine theta. Now, suppose I had switched this and I'd put the x down here and this term up here. Then x would equal a cos theta. So there's more than one way to do these problems. You just got to be careful that you in your accounting. Okay. So that means that dx is going to be a cos theta d theta. So there I've got a new version of the dx. That dx is going to be replaced with this. Okay, now we need to find a new version of the rest of the stuff. What is this? Raise your hand if you know what that square root term is. Got one hand up. Can I get some more hands up? Give me an equation involving that square root term and one of the trig functions. Yeah.
It'd be a cosine.
Yeah, because we get that cos theta, so here's my theta. I always put theta down here. Cos theta is going to be the square root term divided by a, so that the square root term is going to be a cos theta. There's my green thing. So I've got a new version of that. Now, I didn't do this in the fall. Whenever I did definite integrals in the fall, I would always do the indefinite integral completely and then plug in the endpoints. I wouldn't change the endpoints. But for these trig functions, it's often useful to change the endpoints as well. So transform the endpoints. So we have that x equals a sine theta. So when x equals 0, what does that tell us about theta? If a sine theta is 0, what does it tell you that theta has to be? Are you sure? Think about the unit circle. The places on this circle where the y-coordinate is 0, well, so theta is 0. How about when x is equal to a? The other endpoint is, this shouldn't say b. This should say x equals a. So when x equals a, what does that tell you theta has to be? If a sine theta is just equal to a,
Pi over 2.
pi over 2, because that means that sine theta has to be 1, and that's here. So my new endpoints are 0 and pi over 2. So when I substitute all that stuff in, I get theta equals 0 to theta equals pi over 2. This labeling of these endpoints with their variables, the books don't do that, but I think it's actually helpful to remind us that these numbers were numbers about x. These are numbers about theta. So I've got a cos theta, and then I've got dx is a cos theta d theta. So those a's get together, 2 a's on top, 1 a on bottom, so I end up with 4ab times the integral from 0 to pi over 2 of cos squared theta. All right, so there are all sorts of double angle formulas that you should not aspire to memorize. I would just memorize the first one, the most basic ones. So we want to have something that will give us a cos squared theta. So remember that cos of a plus b is cos a cos b minus sine a sine b. I can remember that. And so cos of 2a is going to be cos squared a minus sine squared. Oh, I shouldn't be using a, sorry. Bad form. That's all right. Okay, there's my cos, so let me do cos 2x is cos squared x minus sine squared x. Okay, so I'd like, the reason I want to get, I don't have an integral formula for cos 2x, for cos squared x. I have integral formulas for cos, but not for cos squared. So I need to get rid of this. Well, there's a cos squared. I could rewrite this as cos 2x minus sine squared x, but then I'm stuck having to find an integral of sine squared. I don't have an integral formula for that either. So let's continue. We use the Pythagorean formula to rewrite sine squared as 1 minus cos squared. So we end up with 2 cos squared x minus 1 equals cos 2x. So I end up with cos squared x being 1 plus cos 2x, all that over 2. So all of that goes in over here. So then the 2 comes out, I end up with 2ab times the integral of 1 plus cos 2 theta. So the integral of 1 is easy. And this is from 0 to pi over 2. The integral of 1 is just theta. What's the integral of cos 2 theta? What's an antiderivative of cos 2 theta? So here's where the guess and check method is good. What's an antiderivative of cos theta? Sine theta. So what would be an antiderivative of cos 2 theta? You might think, well, sine 2 theta. Well, let's try that. If I take the derivative of sine 2 theta, I'd get cos 2 theta times 2. Oh, dang it, that's no good. It's off by a factor of 2. So an antiderivative of cos 2 theta has to be sine 2 theta divided by 2. Again, let's check this. Take the derivative of this. The derivative of sine is cos, so I'm going to have cos 2 theta times the derivative of the inner function. That's going to be a 2. And then that's going to cancel the 2 that's in the bottom. And I get a plus c. And then I have to evaluate that from 0 to pi over 2. So I end up with, well, I end up with that whole mess with a pi over 2 inside, and then plus sine of 2 pi over 2 over 2. And then I have to subtract that whole mess with a 0 inside. 0 plus sine of 2 times 0 over 2. Okay, well, sine of 0 is 0, so this term is 0. Sine of pi is also 0. On the unit circle, that's way over here on the far left side. So this is also 0. So all these terms are 0 except for that one. So I end up with pi AB for the area of an ellipse. I love this problem because it's got geometry in it. Area of an ellipse is pi AB. Special case is a circle. So if I have a circle, that's actually just an ellipse where both axes have intercepts A. So I get A equals pi times little a times little a. So in other words, pi a squared. Really cool. This is done in the book, but as an example. And almost never will do an example in class that's done in the book. But this is such a pretty one, worth doing. A final example brings us to part 3. So this should have said part 2 was trigonometric substitutions. So go back and change that. Part 3, integrals that can be done more than one way. So example 6, find this integral. X over the square root of x squared plus a squared. All right, so the book suggests a trig substitution. So the bummer is this is one of your homework problems. And the book suggests this. Suggests saying that x equals a tan theta. So in other words, you do one of those little triangles and you figure out what to do for your substitution. The triangle will tell you that. It would have been better if the book had just said, find this integral using a trig substitution, and then you would have figured that out. But I'm going to do it a different way. Instead, try integration by parts. So I'm going to separate, oops, that should be x cubed. Now I'm going to break off a factor of x. And the reason is, when you take the derivative of a term like the square root of x squared plus a squared, you end up with a chain rule problem. And when you take the derivative of the inner function, the derivative of the inner function is 2x. So taking the derivative of this kind of thing ends up spitting out an x in addition to the square root term. So I just know enough, well, I try a lot of dumb things. That's why I have that notebook. It's full of a lot of dumb things, and some of them work and some of them don't. But so one thing that I know enough to know that it's often helpful to break things off like this. So we have our f equals x squared, and our g prime is x over square root of x squared plus a squared. So my f prime is 2x, and my g is, well, here we go. I'm just going to write this down, and then we're going to do it over to, well, no, I won't. I'll do this over on the side. So how do we figure out what g is? So one method is to integrate. So g is going to be the integral of g prime. So the integral of x over x squared plus a squared, square root. And you're going to do a u substitution. You're going to let u equal x squared plus a squared. And so that means you're going to end up with this. That you've got a new version of the x squared plus a squared. That thing is u. And you've got a new version in one fell swoop of the x dx. That's 1/2 du. So I end up with the integral of 1 over u to the 1/2 times 1/2 du. So that's 1/2 the integral of u to the minus 1/2. So that's going to be 1/2 u to the minus 1/2 plus 1 over minus 1/2 plus 1. So that's going to be u to the 1/2. Sorry, it's going to be 1/2 times u to the 1/2 over 1/2. Well, look, this 2 and this 1/2 get together and they have a party. So I get u to the 1/2, which is just that square root term, x squared plus a squared. So that's what goes here. Now remember I said this is method 1. Actually integrate to figure out what g is. And it's cumbersome. Method 2 is to guess and check. So let's try g equals square root of x squared plus a squared. Then g prime is going to be, well, the derivative, so this is going to be the derivative of x squared plus a squared to the 1/2. I'm sorry, yeah. So that's going to be 1/2 times parentheses to the minus 1/2. So there's the derivative of the outer function. And then I have to multiply it by the inner function derivative, which is 2x. So I end up with 2x over 2x squared plus a squared to the 1/2. So in other words, x over the square root of x squared plus a squared. So it's worth learning, it's worth doing the guess and check method whenever you can. It's easier than doing an integration by substitution. So we know how this integration by parts works. I've got to do the product of those minus the integral of the product of those. So x squared times the square root of x squared plus a squared minus the integral of 2x square root of x squared plus a squared. Well, I'm going to just tell the results of this. You're going to do you're going to do a w substitution. You're going to let w be the thing inside x squared plus a squared. And then that plays out the way substitution integrals play out. It's not a big deal. And you end up with minus 2/3 times x squared plus a squared to the 3/2. There you go. When you do the w substitution. The w substitution works just like this u substitution worked over here. And that makes sense. You can think about this. What if you take the derivative of this? You get 3/2 times parentheses to the 1/2. So the 3/2 cancels the 2/3. But then you have the derivative of the inside function, which is 2x. So that gives you the 2x. So that does work as the antiderivative. So a hard integral using integration by parts. Now, and in my typewritten notes, there's this one that we just did. So it's 2/3 of a page of paper. In my typewritten notes, the solution using the book's suggestion of a trig substitution, I'll show you how long that is. It's this long. It's 1 1/3 pages. So it's a full twice as long solution. So I don't have any wisdom about that. How do you know whether to do one or the other? It's just, that's why, again, get a notebook. And, yeah.
Did we say we'd be getting our test back today?
Yeah, but I'm still talking. Yeah. So, you want to try as many methods as you can. You'll get better at sniffing them out. But again, I don't have any wisdom about how you'll know which is the best way. It doesn't help when the book tells you to do it some way that's actually not a good way. That's a real bummer, I mean, I did it this way. I'm very proud of my solution. It takes up like 2 full handwritten pages in there. But then when I went to help me cheat on my calculushomework.com, found out, well, they don't do it that way. They do it some other way. They just did integration by parts. And I realized, oh, yeah, there is a much easier way, integration by parts. So, all right, so I'm going to hand back quizzes. I think everybody was here for the quiz, so this is how I'm going to do attendance also. Alexandra, Annika,